Alright, so what we're going to look at here is Unit 6, Lesson 11. I know it says 12 here, but I combined a couple of sections before. And there's about 2 or 3 more lessons after this. And we're going to get into something here called the gas laws. And the gas laws deals with mainly 3 variables when it comes to gases: the pressure, the volume, and the temperature. There is a 4th one, which is called number of particles. But I'm going to skip that because it's not something that they normally ask about, and we're just running a little bit short on time, so I just want to get through this. So let's look at one gas law, which involves only the 2 variables, pressure and volume, which is referred to as Boyle's law, but they don't refer to them by name on the Regents exam. So what you have to understand is, what is the relationship between the pressure on a gas and its volume? There's only 2 possibilities. It's either an indirect or a direct relationship, and that's extremely important. So let's take a look at that. So as the pressure on a gas increases, so you're squeezing the gas with more force. If you take a gas and try and squeeze it with more force, what is that going to do to the volume? Well, obviously the volume is going to decrease, and the temperature is constant in there. So that is what we would call an inverse or indirect relationship. And that's what the graph would look like. And you do need to recognize this as being a inverse or indirect relationship, because they literally will ask you about which graph is indirect and which is direct. It's at the bottom. You see, if the pressure on a gas is halved, in other words, if the pressure on a gas is cut in half, keeping in mind it's an indirect relationship, so whatever one does, the other one does the opposite. So if the pressure is cut in half, what would you expect the volume to do? The volume, of course, would double, right? And don't pay attention to the equation, because you're going to see at the end that all the equations for these laws are based on the combined gas law, which is at the end. That's Boyle's law. So example, you blow up a balloon and it expands each time you exhale into the balloon. What happens to the number of gas particles you put into the balloon in each exhale? Well, every time you blow into the balloon, you're adding more gas particles. You're making the volume of the balloon expand. You're also increasing the pressure, because the more particles, you keep in mind, if you could picture this in your head, you're blowing these molecules into this balloon. Those gas molecules are not just standing still inside the balloon. They're moving around inside the balloon at a very high rate of speed. They're colliding with each other, but more importantly, they are colliding with the inside walls of the balloon. And that inside, the collision of those molecules with the inside of the balloon is what actually keeps the balloon expanded. If you're adding more molecules, there's more collisions happening on the inside, which is making the balloon expand. What's the relationship between the gas particles and the pressure? More gas particles, more pressure. Okay, we're going to skip this part here because it's not normally asked about the number of gas particles, and I think it's pretty self-explanatory. As the number of gas particles increases, so does the pressure. I want to get on to the other one. I'm going to go outside here. Okay, it says you blow up a balloon inside the school and bring it outside. It is minus 10 degrees Celsius outside. What would you see happen to the balloon as you stand outside? Well, if you took a balloon and went outside with it on a very cold day, like we had a few weeks ago, the balloon is going to get smaller in size. And that's because the cold air makes the molecules inside contract, move closer together, and they slow down. And because they slow down, there's less pressure inside the balloon. So now the balloon, because it's rubber, tries to get smaller. Once you brought it back inside into the warm air, the molecules in the balloon would get warmer, they'd start to move further out, move faster, and they would increase the volume of the balloon. Alright, let's look at the next one, which is called Charles's law, but don't worry about the name, is temperature and volume. And this is one that's really easy, and we're going to do a lab on this. The easiest way to look at temperature and volume is to look at a balloon. If you take a balloon and you blow it up, tie it off, and then you take that balloon and you put it in a sink of very hot water, what do you suppose is going to happen to it? Well, as the temperature increases, we know that the volume increases. We're not changing the pressure at all. That is a direct relationship. That's what the graph would look like. And again, what happens is when you take that balloon and put it into hot water, the gas molecules inside get warmer. They speed up. They get more kinetic energy. And because they're going faster, they hit inside the walls of the inside of the container harder, forcing the balloon to expand. So the volume is the size of the balloon. If the balloon gets bigger, you're increasing the volume. And there's a question at the bottom: if the temperature of a gas is halved, if you cut the temperature in half under constant pressure, what will happen to the volume? Well, since they're a direct relationship, if you cut it in half, the volume will also be cut in half. That's what a direct relationship is. we're going to skip this. All right, here's the next law. This is what's called Lusak's law, and now it's temperature and pressure. It has the same relationship as Charles' law. As the temperature increases, we already know that the pressure inside the balloon increases. We're going to keep the volume constant. So if you take a balloon and you increase the temperature of the gas, what the balloon is going to want to do, it's going to want to expand. But if you keep it from expanding, what's going to happen is the pressure is going to increase. It's like if you take a spray can and you heat it, that's very dangerous, because what's happening is, in essence, is what we just talked about. You're heating the gases inside the metal container, but the volume of the container cannot expand. It's a solid, it's a very stiff container. What eventually will happen is that the pressure inside will build so much that it will literally explode. And that's a direct relationship. We're not worried about the equation. Okay, if the temperature of the gas is tripled, the pressure will also triple. Okay, and that's it for this one, and we'll leave the combined gas law for